Welcome to today's session on Big Data Analysis with Dask. We'll explore how Dask empowers us to handle massive datasets with ease, leveraging distributed computing principles. Whether you're scaling beyond a single machine or optimizing workflows, Dask bridges the gap between simplicity and scalability. Prepare to revolutionize your data workflows. In this chapter, we're diving into the core reasons why Dask is a game changer for data processing. We'll discuss common bottlenecks with traditional tools like Pandas and NumPy and demonstrate how Dask overcomes these limitations. By the end of this chapter, you'll clearly see why Dask is a must-have tool for handling today's ever-growing datasets. Before we get into Dask, let's start by understanding where traditional data analysis tools like Pandas and NumPy struggle. While they are excellent for small to moderate datasets, they aren't designed to handle the scale and complexity of modern data challenges. From memory constraints to the lack of parallelism, these limitations set the stage for why Dask is essential. Let's break this down. Pandas and NumPy are fantastic for small-scale data operations, but the challenges become apparent when your data or computations grow in size or complexity. For instance, you've probably tried loading a massive dataset into Pandas only to watch your system crawl or crash due to memory issues. Similarly, the lack of parallel or distributed computation makes these tools struggle to fully utilize modern multi-core systems or distributed environments. Parallel processing is essential in the era of big data. Think about it this way. If we have a massive dataset that a single machine struggles to load, dividing the workload across multiple CPUs or machines allows us to process the data quickly, efficiently, and without crashing. It's like assigning different parts of a giant puzzle to many people instead of solving it alone. This ensures maximum resource utilization and lets us push past typical memory bottlenecks. This section introduces the problems that traditional tools face when managing data at scale and explains how Dask solves them. We're setting the stage to understand why Dask is a game changer in distributed computing. Dask tackles big data challenges step by step. It uses smart techniques like chunking, splitting data into smaller pieces that can be processed independently. This, combined with its ability to work on everything from your laptop to a high-performance computing cluster, makes Dask highly versatile and powerful. I always say Dask is like upgrading from riding a bike to driving a sports car: speed, efficiency, and scalability all bundled into one. This section highlights the unique advantages Dask offers compared to traditional tools. It's about understanding why Dask is worth considering for any data-intensive project. Dask is meant to bridge the gap between ease of use and high computational power. Highlight its compatibility with well-known Python tools like Pandas and NumPy. Emphasize how Dask allows you to work with datasets that previously exceeded hardware limitations while providing smooth scalability for small and large projects alike. The Dask task graph is central to how Dask achieves its scalability. Use simple examples, such as breaking a computational process into smaller parts with clear dependencies to explain how tasks are scheduled on demand. Mention that this approach avoids bottlenecks by distributing work efficiently. This is where Dask's power really shines. In this example, we use Dask delay to create a computational pipeline. The visualize it function helps us inspect the task graph, showing the dependencies between tasks. You could mention that this graph is useful in debugging and optimizing workflows, especially in large-scale distributed applications. This table lays out the key differences between Pandas and Dask, stress how Pandas is great for small datasets that fit in memory, while Dask extends those capabilities for large distributed datasets. Lazy evaluation and cluster support are significant differentiators. Use this slide to inspire confidence in Dask's ability to scale workflows efficiently. In this comparison, highlight the practical scalability difference between Dask and Pandas. Point out how Dask is especially valuable for handling datasets larger than available system memory thanks to its chunking and parallel processing capabilities. Encourage participants to picture using Dask in real-world scenarios such as aggregating data from financial reports or user logs. Elaborate on each application. For example, in financial analysis, discuss trading and forecasting large datasets. For climate simulations, mention analyzing satellite data. In machine learning, give examples like training deep learning models or automating feature engineering pipelines. Relate this to participants' existing workflows. Now let's discuss what type of professionals or teams might benefit the most from adopting Dask. This will help participants contextualize Dask's utility in their own work. Emphasize the tool's relevance for anyone facing growing data challenges. During this discussion, remind participants that Dask is not limited to enterprises with huge budgets. It's also valuable for small teams, researchers, or individual analysts who simply need a low barrier way to scale their workflows without becoming distributed computing experts. Emphasize how Dask complements familiar tools like Pandas, NumPy, and scikit-learn, making it accessible to existing data practices. In this chapter, we'll break down the two main pieces of Dask architecture, its core collections and its schedulers. Together, they enable Dask to scale computations efficiently. Whether you're on your laptop or a distributed cluster of machines, think of collections as your data tools and schedulers as the machinery behind the scenes that make everything come together seamlessly. Let's first clarify the fundamental building blocks of Dask collections and schedulers. Collections act as scalable versions of the tools you're already familiar with, like Pandas or NumPy, while the schedulers handle task scheduling and execution. We'll explore how these two components work in harmony. Let's start with something familiar, the Pandas data frame. Dask data frame looks and feels just like Pandas, but here's the twist. It works even when your data is too big to fit in memory. Imagine trying to analyze a 10 GB CSV file. Pandas would choke, but Dask. It slices that file into small pieces and processes them in parallel. The best part, you use almost the same syntax as Pandas. It's like upgrading your bicycle to an electric bike. Same pedaling, way more power. Now let's talk numbers. If you're used to NumPy, Task Array is your new best friend. For big number crunching, think of a giant matrix like 10,000 by 10,000 numbers. Dask splits it into byte-sized blocks and computes them across multiple cores. It's like slicing a cake and letting your whole team eat at once. Great for large scale simulations or scientific computing where NumPy just can't keep up. Not all data is neat and pretty. Sometimes you're dealing with messy logs, JSON, or raw text. That's where DaskBag comes in. Think of it like a backpack full of unorganized files. With simple map and filter operations, you can clean, transform, and count things like how many errors appeared in log files. It's basically your toolkit for making sense of chaos. This one's for power users. Dask Delayed lets you build your own workflows step by step. You mark functions as a delayed, and Dask builds a task graph behind the scenes. It's like making a blueprint first and only building the house when you're ready. Perfect when your logic doesn't fit into a data frame or array, like combining results from multiple APIs or custom file processing. All this magic, splitting, processing, and combining, doesn't happen by itself. Meet the scheduler tasks behind the scenes manager. It breaks your work into tasks, assigns them to workers, and makes sure nothing crashes. Think of it as a conductor in an orchestra. It doesn't play an instrument, but keeps the whole symphony running smoothly. Without the scheduler, everything would be chaos. Dask offers different schedulers, and you can pick the one that fits your workload. For debugging, use the single-threaded scheduler, slow but transparent. For I/O-heavy tasks, try multi-threading. For CPU-bound number crunching, go with the process-based option. And when you're ready for serious power, the distributed scheduler lets you run computations across a whole cluster. The good news: you don't need to rewrite your code. Just start a client, and Dask takes care of the rest. In this section, we'll explore the core mechanism behind Dask, the task graph. The task graph is central to how Dask optimizes computations, manages dependencies, and executes tasks efficiently across resources. We'll break down its components, execution workflow, and why it's so powerful for distributed computing. Explain the concept of a task graph by comparing it to a to-do list where some tasks depend on others being complete. For instance, cooking a meal starts with gathering ingredients, chopping vegetables, and then cooking. Dask's task graph optimizes and schedules the steps, ensuring each is completed as soon as dependencies are met. Learners should also grasp the real-world importance of minimizing data transfer and parallelizing independent tasks. Walk through the example code to show how Dask constructs a simple task graph. Highlight the use of Dask delay to define tasks and show how Z visualizing generates a diagram of the task graph. Reinforce the idea that computation doesn't occur until the compute is explicitly called, making the process efficient and controlled. In this chapter, we shift our focus to Dask data frame, one of Dask's most commonly used collections. This tool extends the familiar Pandas API to handle datasets that are too large for memory, enabling efficient parallelization and scalability. By the end of this chapter, learners will understand how to leverage Dask data frame for real-world scenarios where Pandas falls short. This section introduces the fundamental features of Dask data frames and explains how they extend the familiar Pandas API while overcoming its limitations. We'll see why Dask is essential for analyzing datasets that exceed memory capacity and how its lazy evaluation approach boosts efficiency in processing large-scale data. Highlight the similarity between Dask data framing and Pandas to make it approachable for users already familiar with Pandas. Emphasize how Dask's ability to handle out-of-core computations and lazy evaluation enables seamless scalability for workloads that Pandas cannot support. Use the code example to clarify how lazy evaluation works in contrast to Pandas' immediate computation style. Highlight the similarity between Dask data frame and Pandas to make it approachable for users already familiar with Pandas. Emphasize how Dask's ability to handle out-of-core computations and lazy evaluation enables seamless scalability for workloads that Pandas cannot support. Use the code example to clarify how lazy evaluation works in contrast to Pandas' immediate computation style. Here's a practical example of how Dask efficiently handles large CSVs by splitting them into smaller chunks for processing. Note that while Dask delays execution, During operations like Group E, computation is only performed when a compute is invoked. Walk participants through this workflow, emphasizing its scalability for big data use cases. Lazy evaluation is a cornerstone of Dask's efficiency. Explain how it works behind the scenes by creating a task graph that outlines all dependent operations. This not only ensures fewer redundant steps, but also lets Dask intelligently execute tasks with minimal resource consumption. Use the provided diagram to reinforce how a task graph visualizes Dask's internal optimization. Lazy evaluation is one of Dask's most powerful features. It waits until you're ready to compute, which lets it optimize your entire workflow. Think of this like planning a road trip where you optimize stops beforehand instead of making random detours. Highlight how delaying computation saves memory and ensures only necessary calculations take place, especially for learners working on memory-intensive tasks. In this example, learners will immediately notice the difference between a lazy representation and actual computation. First, Dask describes the computation but doesn't execute it, which is evident by the metadata output. Once we call compute, we get the actual results. Encourage learners to experiment with larger chunk sizes and observe how lazy evaluation optimizes memory usage for larger datasets. Introduce Dask Array as a solution for numerical computations that go beyond NumPy's memory limits. Emphasize its efficiency and scalability through block-wise operations, particularly for workloads involving massive datasets such as climate modeling, finance, or any high-dimensional numerical data. Dask Array extends NumPy, but with significantly enhanced scalability. Explain how it divides an array into chunks or blocks, distributing them across processing units for parallel execution. Relate this to a scenario like processing 4K video frames, where you can handle components independently to reduce bottlenecks. Invite learners to think of Dask Array as their go-to tool when arrays no longer fit the memory constraints. Explain that block-wise operations are the backbone of Dask Array's efficiency. Compare it to breaking a large task EOG, cleaning your entire house into smaller, manageable parts, cleaning one room at a time. Each block can be processed independently, enabling faster parallel computation and better utilization of available resources. Highlight that Dask Array is ideal for performing computations on datasets larger than RAM. Unlike NumPy, Dask facilitates parallel, distributed computations and works seamlessly with chunks of data, making it a great choice for large-scale numerical tasks. Point out that the compute method triggers the actual computation after constructing the task graph. Emphasize the importance of chunks. Smaller chunks allow better parallel computation, while larger chunks reduce overhead. Experiment with chunk sizes to meet the demands of available memory and CPU cores efficiently. Introduce DaskBag as a versatile tool for handling messy, unstructured data like server logs, JSON files, or textual data. It excels in scenarios where traditional structured data processing tools like Dask Data Frame or Dask Array fall short. Mention that it adopts a functional programming style, enabling map, filter, and reduce operations in parallel with minimal effort. Introduce DaskBag as a powerful solution for processing unstructured or semi-structured data. Start by explaining how DaskBag differs from other collections like Dask Data Frame or arrays, which focus on structured, tabular, or numerical data. Highlight how common tasks, such as parsing logs, analyzing JSON files, or processing text, can be parallelized easily with functional programming primitives like map and filter. Walk through this real-world example of processing logs. Explain that a DB read text loads the log files lazily, processing them in chunks under the hood. Discuss how filter applies a lambda function to filter out lines containing the keyword error and count aggregates the results. Finally, mention how the compute triggers the actual execution, scaling seamlessly across resources. Emphasize the simplicity of structuring a log analysis workflow using Dask. Relate this to practical scenarios like analyzing server logs for debugging. Discuss the power of using lazy evaluation here. Dask processes only relevant chunks of the data, optimizing memory usage and execution time. Encourage learners to think about scalability when processing unstructured datasets. Introduce the chapter by highlighting the flexibility of Dask, delayed for building custom, fine-grained parallel workflows. While dust collections like DataFrame or Bag abstract away much of the complexity, delayed allows advanced users to define task pipelines manually, useful for unique computation patterns or when integrating external libraries. Introduce Dask. Delayed as a flexible tool that empowers users to parallelize even highly customized workflows. Emphasize its versatility for tasks that don't align with traditional dust collections like data frames or arrays. Use an analogy like an assembly line where each task depends on the previous station to convey the concept of dependencies explicitly. Walk through the use of delayed step by step. Start with a real-world analogy, e.g., preparing ingredients independently in parallel for a recipe. Explain how each data point creates a node, how summing results forms the dependency, and finally how computation is only triggered when calling a compute. Emphasize the ability to visualize and understand task flow using final visualize. Display this task graph image to illustrate how Dask splits tasks into nodes and dependencies. Highlight how this graph represents the flow. Independent tasks, cell-like individual multiplications, feed into a final dependent task summation. Point out that understanding the graph helps debug and optimize execution. Here, connect the concept of task graphs to practical examples. Explain that each transformation S, like multiplying numbers, creates a node, while edges outline dependencies such as summation waiting for all multiplications to complete. Tie the visual aid graph back to the code example. Pose rhetorical questions like, what happens if a node fails? How does this graph help us debug? This encourages thinking about fault tolerance and task optimization. In this chapter, we'll explore how Dask enables distributed computing for handling large-scale workloads. The focus will be on understanding how Dask clusters operate and scale across multiple machines to maximize computational efficiency. Let's dive into the architecture of a Dask cluster. This includes a clear understanding of the key components, scheduler, workers, and client, and how they seamlessly interact to execute distributed tasks effectively. The scheduler is essentially the nerve center of a task cluster. Think of it as a conductor leading an orchestra, ensuring every instrument sever, or in this case, worker plays its part at the right time. The workers take on the intense computations, while the client acts as the user interface, where you control the workflow and monitor progress. To help visualize, imagine the client as a manager delegating work to the scheduler, which acts like a dispatcher breaking the work into smaller double chunks, tasks. Workers, as the gritty task achievers, execute these tasks and report back to the scheduler. This scalable collaboration ensures large computations are broken down and optimized effortlessly. This code snippet shows how to start a local Dask cluster on your machine. The cluster will utilize 4 workers, with 2 threads per worker and limit each worker's memory usage to 2 GB. Once the client starts, it outputs a URL link to the Dask dashboard, a powerful interface to monitor and debug your tasks in real time. Encourage learners to explore the dashboard to understand how tasks are distributed and executed. This hands-on step ensures learners get familiar with managing resources effectively. Transitioning from local execution to distributed clusters allows Dask to perform at scale, leveraging multiple machines for larger workloads. In this section, we explore how Dask integrates with distributed environments such as cloud platforms and high-performance computing systems. Highlight the flexibility Dask provides for seamless scalability, whether you're working locally, on a private cluster, or with public cloud infrastructure. Distributed clusters are the key to scaling Dask workflows. Discuss how cloud platforms such as AWS or GCP provide elastic scaling for complex workloads. Introduce Dask Gateway, a tool designed to create and manage clusters easily, making Dask accessible in enterprise or team environments. Emphasize the importance of distributed computing for projects that involve high data volumes or computationally intensive operations, such as simulations or machine learning pipelines. This script demonstrates how to connect to a pre-existing distributed Dask cluster. The scheduler address specifies the location of the scheduler coordinating the cluster. Ensure learners understand the role of the scheduler as the central hub that manages tasks and resources. Highlight that once connected, users can utilize the same Dask API as they would locally, making distributed programming nearly identical to single machine workflows. Encourage learners to inspect the Dask dashboard via the link provided by the client to monitor the performance of the distributed cluster. The Dask dashboard is incredibly useful for understanding what's happening under the hood of distributed computations. For example, if you're working on a task and notice memory spikes or uneven task scheduling, the worker resources or task stream tabs can pinpoint these issues. Take some time to explore the dashboard during different stages of your computation. Showing a live demo or screenshot at this point would help reinforce the importance of these tools. In this chapter, we focus on putting theory into practice to solidify our understanding of Dask. We'll work with a real-world dataset, the NYC taxi trip dataset that is both large and widely used in distributed computing benchmarks. The goal here is to showcase the power of Dask for loading, cleaning, and analyzing data, and for building machine learning models. By the end, you'll understand how to handle massive datasets with ease. To kick off any analysis project, especially one involving scalable computation, it's essential to clearly define our objectives and set up the necessary tools. This section will walk through our project goals, introduce the NYC taxi dataset, and explain why it's an excellent candidate for demonstrating Dask's capabilities. We'll also ensure we understand the infrastructure requirements for handling such a large dataset. The NYC taxi trip dataset is a great benchmark for testing distributed computation because of its scale and variety. Its real-world relevance also makes the outcomes engaging. You'll be analyzing patterns that could inform city planners, ride-sharing services, or financial analysts. In this step, we'll frame the dataset and objectives. Emphasize that our final deliverable is not just analysis, but also actionable insights and experience with scalable tools. In this step, we are using Dask to load the NYC taxi dataset. What makes Dask powerful is its ability to handle data that might exceed your computer's memory. Instead of loading the entire dataset into memory like pandas, Dask only reads the metadata and processes the data in chunks. This approach minimizes memory usage while ensuring scalability for large datasets. The headout function lets us quickly preview part of the data without triggering the loading of the entire file. Okay, now this part is about ETL. ETL means extract, transform, and load. It's a process used to move and prepare data from one place to another, especially for analysis or storage. ETL is an essential process in data preparation. When working with large datasets like the NYC taxi data, traditional tools like pandas may struggle due to memory constraints. Dask's chunk-based execution model distributes these operations across multiple cores or machines, making it possible to handle large datasets efficiently. In this example, we are focusing on cleaning steps such as removing nulls and filtering anomalies, which ensures the dataset is reliable for downstream analysis. Here we're performing two key ETL tasks using Dask. First, we remove rows where the fared amount column contains missing or null entries. This ensures the integrity of our analysis. Next, we compute the average fare grouped by the passenger count column. Thanks to Dask's parallelized data processing, these operations can scale efficiently for datasets too large to fit into memory. Notice that eComputed is used to trigger the actual computation and fetch the result. Without this, Dask will only build the task graph for deferred computation. In this section, we'll explore how to build a machine learning pipeline using Dask ML, which is specifically designed for working with datasets that are too large to fit into memory. This will demonstrate the scalability of Dask in training, testing, and evaluating ML models on distributed data. Explain that traditional ML tools like scikit-learn work well for small datasets, but can struggle with larger than memory data. Dask ML addresses these challenges by breaking operations into parallelizable tasks, making it ideal for handling extensive datasets. Here, we're using Dask ML to train test a split to split a massive dataset. Note how Dask converts data frame columns into Dask arrays with chunking for scalable operations. The logistic regression class mirrors the interface of scikit, learn, emphasizing ease of use, and its distributed backend handles large-scale data efficiently. Highlight how Dask handles computations on larger data without exhausting memory. This chapter focuses on practical tips to maximize the performance of your Dask-powered workflows. We'll discuss strategies like optimizing file formats, tuning chunk sizes, and monitoring tasks using the Dask dashboard. These techniques ensure efficient resource utilization and faster computation times. In this section, we'll explore techniques to optimize Dask's performance, focusing on file formats and chunk sizes. These strategies are essential for scaling computations efficiently and ensuring tasks complete quickly without exhausting resources. Let's dive into practical recommendations and best practices. CSV files are simple and widely used, but their row-based structure leads to slower read and write speeds, especially for analytical tasks. Parquet, on the other hand, allows you to work with data in a columnar layout, particularly important when working with selective columns in large datasets. Additionally, it's easy to integrate Parquet into Dask workflows, as we'll see in the next example. Here we demonstrate how straightforward it is to save data as Parquet and read it back into a Dask data frame. Notice how the toParquet and readAParquet methods replace the CSV equivalents seamlessly. After saving, you'll benefit from faster reads, optimized query performance, and reduced disk space usage. Encourage the audience to test both formats and observe the performance improvement. Chunk size has a direct impact on Dasek's parallelism and performance. A chunk that's too large can overwhelm memory and lead to out-of-memory errors, while excessively small chunks increase scheduling delays. Balancing these factors is key, and tools like the Dask dashboard will provide real-time insights into memory usage and task execution. Encourage experimentation to find the sweet spot for your environment. The Dask dashboard is your window into the computational process. Show students how to open the dashboard URL, typically displayed when you initialize a Dask client. Explain how the task stream panel highlights execution bottlenecks, while the resource utilization panel displays memory usage and CPU load per worker. Encourage learners to use the Graph tab to get a deeper understanding of task dependencies, which can help them debug and improve resource allocation. Good job! We've now reached the final chapter of our Dask journey. Let's reflect on the key ideas. Start by reminding participants that Dask addresses core limitations in traditional tools like Pandas and NumPy, especially for large, scale, or distributed data workflows. Reinforce the three pillars of Dask: lazy evaluation, task graphs, and flexible scalability across machines. Encourage the learners to think about how these features can be applied in their current or future projects. Now is the time to challenge them. What parts of their current workflow could benefit from parallelism or chunk-based processing? Close with motivation. Adopting Dask doesn't require abandoning familiar tools. It extends them. Remind them of the rich Dask documentation, growing open source ecosystem, and community support. This is just the beginning. Invite them to explore further, experiment boldly, and build smarter data pipelines. Use this cheat sheet as a quick reference when you apply Dask in your own projects. It summarizes the most important technical concepts that you should retain from this course. Encourage learners to print or save this slide for future use. Motivate participants to experiment with what they've learned. By applying Dask in real scenarios, they'll gain confidence and see how powerful distributed workflows can be. Start small and scale as needed. Use this slide to prompt a short reflection or open Q&A. These questions aim to stimulate deeper thought about architecture decisions, performance tuning, and real-world integration, ideal for in-person or online group discussion. Encourage learners to continue exploring Dask through tutorials and community resources. Point out that Dask scalability and flexibility make it suitable for both individual analysts and enterprise-level teams. Learning never stops. Keep experimenting. Wrap up the session on a warm and reflective note. Invite participants to provide feedback via survey, email, or post-session form. Feedback is essential for improving the experience and tailoring future content to learners' needs.